Hi there, Mr. Sutton here, bringing you the AB Calculus 6-3 Extra Practice Number 3 solutions on slope fields. On this free response problem, we have this differential equation given to us, and our first task is to figure out the slope field just for the 6 points they gave us here. I'm going to set up a little table that has those x and y values in it. So in my table, I've got the x values 0 and 2, because those are the only two where they actually put dots, and also the x values 0, 1, and 2. So let me just go down each column and come up with the numbers based off of my differential equation. So for this first column, this is where I have x values of 0. So this is going to be, basically your denominator is just going to be -1 for everything in this column, and you're doing the y value squared over -1. So this is 2 squared over -1, which is -4. 1 squared over -1 is -1, and 0 squared over -1 is 0. Next, this column right here, this is where x equals 2. So if x is 2, your denominator is going to be 2 minus 1, so just 1 the whole time. So we're really just doing the y value squared over 1 for this second column. So that's going to be 2 squared over 1, which is 4. 1 squared over 1 is 1, and 0 squared over 1 is 0. Now I'm just going to use these slopes to draw some tangent lines up here. So we have a -4 tangent line right here. Just draw it as best you can. So you're going basically down 4 and over 1, so pretty steep. And this next one is just down 1 and over 1, so draw this less steep. This one, there's no wiggle room. You have to draw a horizontal tangent line because this is 0 slope. And then up here, this is going to be +4, so that's very steep in the positive direction. And then we have 1 less steep in the positive direction, and finally another horizontal tangent line for this slope of 0. On this part of the problem, they're saying f of x is the particular solution to this differential equation, initial condition of 2, 3. We want the equation of the tangent line for y equals f of x at 2, and then use that to approximate f of 2.1. All right, so I'm going to use my general tangent line setup here. So I have L of x equals, in general, f of a plus f prime of a times x minus a. Now applying this to the specific problem, the a value in this case is the x value 2, because that's where everything is kind of centered. That's our point of tangency. So really I'm looking for something in the format of L of x equals f of 2 plus f prime of 2 times x minus 2. And I really just need to figure out f of 2 and f prime of 2 to write the equation of this tangent line. Well, f of 2 I actually already know. They gave it to me. That's 3. For f prime of 2, I have to take 2 and plug it into this differential equation to get the slope there. But this is a little bit tricky because this differential equation takes not just x values but also y values. So I'm going to have to plug 2 in for the x right here. I'm also going to have to plug in the y value that goes with 2, which is 3, into this y squared part. So here's what f prime of 2 looks like then. It's going to be 3 squared, the y value 3 squared, over the x value 2 minus 1. So this is 9 over 1, which is just 9. Plugging things in now, we have L of x equals 3 plus the slope we just found of 9. And then we have x minus 2 there. And now for the last part of this, they want us to use this tangent line to approximate f of 2.1. So I'll say f of 2.1 is approximately equal to 3 plus 9 times 2.1 minus 2. Notice I wrote approximately equals here, not regular equals. That's important. And since I have all constants, I don't actually have to simplify this. I could just leave it the way it is. But if I wanted to simplify a little bit, 2.1 minus 2 is 0.1, times 9 is 0.9, so we have 3 plus 0.9, which comes out to 3.9. For this last part of the problem, they want the particular solution to this differential equation using this initial condition. So this is kind of your standard diffie-q dance here. Now, because we have an output variable, this y here, in the differential equation, that means we will have to separate our variables before we take any antiderivatives. So let me do that by dividing both sides by y squared to get it with the dy. So I'm going to just write this as y to the -2 times dy, although you could write dy over y squared, but this sets me up to use my reverse power rule a little bit sooner. And now I can do dx times both sides to get it on the other side. So we have dx over x minus 1, or x minus 1 to the negative 1 dx, either way. Taking my antiderivatives, this first one bumps up to a negative 1. Dividing by that, we have negative y to the negative 1 on the left side. And on the right side, this is just going to be ln absolute value of x minus 1. And don't forget the plus c. Now we actually have to find that c value because we're doing the particular solution, not the general solution. So to get the c value, we plug in this initial condition. So we have negative y value of 3 to the negative 1. And over here we have ln of the x value 2 minus 1 plus c. So let's see here. This is ln of 2 minus 1. That's just ln of 1, which is just 0. So we just have c on the right side. And c is going to equal what? Well, on the left side, this is just negative 1/3. So that's the c value then. Before I plug that back in, I have to resolve this absolute value because we're not allowed to have that in a particular solution. So to figure out what we have to do with this absolute value, we look at the initial condition where I notice that the x value, which is what's inside this ln here, the x value is 2. So if x equals 2, then this x minus 1 expression is going to come out positive, which is telling me I don't need to do anything special for the ln to avoid negative numbers. I don't have to like multiply by a negative 1 or anything in there. I can just rewrite this as ln of parentheses x minus 1 and I'll be all set. So let me do that now. We have negative y to the negative 1 equals ln parentheses x minus 1. And then you have the plus c, which in this case is minus 1/3. At this point, all there is left to do is isolate y. So let me start by dividing everything by a negative 1. So basically, I'm reversing the order of subtraction on the right side of the equation. And before I flip everything here with the negative 1 power, I'm just going to merge this into one fraction to make it a little easier. So common denominator of 3, this is going to be 1 minus 3 ln x minus 1 all over 3. And now let me just take the reciprocal of both sides to get y. So y is going to be 3 over all that stuff in the numerator. And this is as good as it gets. For this problem, I'm trying to make a slope field for this differential equation. So I'm going to start by making a table of slope values based off the x and the y values in this grid. So I've got the x values going from negative to positive 2. Same thing with the y values, actually. And although none of the x values, zeros, are really getting dots here, I'm going to include them in my table anyway. There's no need to, but I just happen to throw it in. So let's go through each column now. For this first column, this is where the x value is negative 2. To make my life easier, I'm going to kind of include this negative here with the x value. So negative 2 means I just have 2 that I'm dividing each of these y values by. So we have 2 over 2, which is 1. 1 over 2 is 1/2. 0 over 2 is going to be 0. In fact, this whole row is going to be zeros. Then we have negative 1 over 2, so negative 1/2. And negative 2 over 2 is negative 1. Next, I'm dividing all these y values by, let's see, negative, so essentially dividing by 1. So basically, I'm just getting the y value I started with then. So we have 2, 1, 0, negative 1, and negative 2. Next, I'm doing basically all these y values divided by 0, which is going to be undefined for everything in this entire column, all undefined. So I don't have to put anything on the graph for this. And then I'm going to be dividing by negative 1 essentially for all these y values. So we have 2 over negative 1, which is just negative 2, 1 over negative 1, 0 over negative 1, negative 1 over negative 1 is positive 1, negative 2 over negative 1 is positive 2. So pretty much the reverse, the opposite of everything in this negative 1 column. And now this positive 2 column is just going to give me everything I got in the negative 2 column, but with the signs reversed, because that's the only difference here. So this is going to be negative 1, negative 1/2, 0, positive 1/2, and positive 1. All right, graphing all of that now, we have up here in the upper left a slope of 1. Then we have 1/2, so up 1 over 2 kind of slope. Then 0 is going to be perfectly horizontal. Then negative 1/2 and negative 1. Next we have 2, so steeper than 1. And then we have 1. We've got 0, negative 1, negative 2. Nothing in the on the y-axis because those were all undefined. Over here now we basically have the symmetrical version of what we had in this negative 1 row. So negative 2, negative 1, 0. This is now going to be positive 1 and positive 2. And in our x equals 2 column here, we've got negative 1, negative 1/2 is a little less steep, 0, 1/2, and finally 1. For this problem, I'm trying to take this differential equation and make a slope field out of it. So let me set up a table that has all the x and y values in this grid, and I'm going to lay them out exactly how these are laid out. So here's negative 2, 2. Down here is 2, negative 2, just corresponding to my grid here. So I'm going to go column by column. This first column, I have all the x values being negative 2. So we basically have negative 2 times all these y values. So we're going to have, let's see, negative 2 times 2 is negative 4. Negative 2 times 1 is negative 2. Negative 2 times 0 is 0. And then we have positive 2, positive 4. For this next one, I have negative 1 times all the y values. So we've got negative 2, negative 1, 0, 1, and 2. Next, we have 0 times all the y values. So this is going to be 0 all the way down for every single one of these. No need to overthink it. Now we have 1 times all the y values. So we just have 2, 1, 0, negative 1, and negative 2. And finally, we have 2 times all the y values. So pretty much doubling everything in this one column. So we have 4, 2, 0, negative 2, and negative 4. Okay, let's put all those tangent lines in here now. So this is negative 4, pretty steep. Negative 2, less steep. 0 is a horizontal line that has to be drawn perfectly horizontal. Then we have positive 2, and more steep than that, positive 4. On to the next column, this is negative 2. Negative 1 is less steep than negative 2. Then we have 0, 1, and 2. Everything on the y-axis is horizontal because those are all slopes of 0. So again, no need to overthink this too much, just all the way down. And now let's see, slope of 2 up here, slope of 1, 0, negative 1, and steeper than that we have negative 2. And then for this last column, positive 4 is the steepest of all there. Then 2 is a little bit steep, 0, negative 2, and steeper than that we have negative 4. For this problem, I'm trying to figure out which of these differential equations could represent this slope field. So I'm going to start by looking up a few slopes off the slope field and seeing which of these answer choices are able to hold up when I plug those coordinates into the differential equation. So let me start with 0, 0. That's kind of my favorite point to test first. At 0, 0, looking in the slope field, there's nothing there, which tells me that the slope should be undefined at 0, 0. Now looking at what happens if I actually plug 0, 0 into these differential equations, choice A, 0 times 0 is 0, so that's not undefined. So choice A does not give us the result that we wanted. Choices B, C, D, and E, you're going to end up with 0, 0 in all 4 cases, all undefined, so we can't eliminate anything else. So let's test out now an x and a y value that are different, like 1 and 2. Looking up 1, 2 in the slope field here, I have a slope that is, well, it's negative at the very least. It's kind of hard to tell exactly what it is, but it's negative, and it's definitely a slope that is not as negative as negative 1. So this is actually greater than negative 1. It's somewhere between negative 1 and 0. Maybe it's negative 1/2, but I don't know for sure. I'm certainly not going to bet any money on that being negative 1/2. But now let's see what I can eliminate in my answer choices. So let's see, A was already gone. B, this would end up being 1 over 2, which is a positive number. So we can eliminate B. Same thing with E, that's also going to come out positive. So really it's down to C and D. With C, I've got negative 1 over 2, which is plausible. With D, I would have negative 2 over 1, which is too steep. So I can eliminate B, D, and E, which leaves me with only choice C. On this one, I'm trying to figure out which of these differential equations matches this slope field. So let me start by testing out the point 0, 0 in the slope field. So looking that up in the slope field, we have a horizontal tangent line there telling me that my slope should come out to 0 when I plug 0 and 0 into the differential equation. Taking a look at the options here, choice A would give us 0 over 0, which is undefined. Same thing with choice B, so A and B can both be eliminated. And then choices C, D, and E will all give us 0 if we plug 0 in for X and Y. So those are all still in the running. All right, at this point, let's see here. I've got multiplication versus subtraction versus addition. So let me just try something that's not 0, like 1 comma 1. So in the graph, 1 comma 1 here has a positive slope. I'm not sure exactly how positive it is, but at the very least, it's steeper than 1. 1 would be less steep. 1 I can definitely tell. Like 0 comma 1, this looks to be a slope of 1. At 1 comma 1, that looks like it's bigger than 1. So based off of that, let me see what these answer choices are doing for me. So A and B we already eliminated. C, this would be 1 minus 1, which is 0. So we can get rid of that. Choice D, this would be 1 times 1, which is a slope of 1. That doesn't seem steep enough. Choice E, we would have 1 plus 1, which is bigger than 1. So it looks like choice E is the only one that still makes sense. C and D can then be eliminated, so I'm just going to pick choice E. On this problem, we are given a slope field, and we want us to draw a solution curve with the initial condition -4, -1. So first condition you have to meet is your curve has to go through the point -4, -1 right here, and then it just has to follow the tangent lines as best you can. So we're pretty much at the edge of the graph. We just have to go to the right here. If we follow these tangent lines, it looks like it's doing this kind of thing right here. There's only a couple tangent lines we can actually follow, but that ought to do it, or you could even make it a little more steep. There's kind of a little bit of wiggle room in here as long as you're going through this point and more or less going in this direction.